Measures of spread, section 2.1. Fran has exam scores of 71, 81, and 91. Sandy has exam scores of 80, 81, 82. Both students have the same mean and median, but the mean and median are both 81. But Fran's scores are more spread out. So we wanted to take a look at measures of spread, measures that tell us how spread out a data set is. We've already looked at range and interquartile range, or IQR, and now in this video here we're going to look at variance and standard deviation and coefficient of variation. These are a little bit harder to compute, but they are very important. So the formula for the sample variance, sample variance is denoted as squared. It's a summation as k goes from 1 to n. This is sigma notation again. The quantity xk minus x bar, quantity squared, all over n minus 1. And it's going to be helpful to put the intermediate steps into a table. And this formula kind of tells us the order of operations. We want to first do what's inside parentheses. So column 1 we want to list each score, and then the second column will be each score minus the mean. That's what's inside parentheses. That's the first computation that we want to do. And then the third column we can square the values that are in the second column. So that's the exponents come before a long division or a sum. And then we can want to compute this column 3 total. So this sum means sum. I think sigma means sum. That's this column 3 total, and then divide by n minus 1. Okay, so here I've put together a table. The first column is the values of x, and we already computed the mean. The mean was it was 70. I think it was the total of 912 divided by 12. But the total here, I didn't put down the total, but I think it was 912. And if we divide that by 12, x bar 912 divided by 12 is divided by 12 equals actually it wasn't 912. Let's add these up. So this is 80 plus 88 plus 28 plus 91 plus 65 plus 88 equals plus 83 plus 59 plus 92 plus 78 plus 89 plus 82 equals 923. 923. So it's 923, and then divide that by 12. And I get 76.91 and repeating sixes. Okay. So let's store this in memory. So do stow and then equals, so it goes into memory A. And then okay, so let's do so I fill out the table except for the bottom 2 rows. So let's do the bottom 2 rows. So it's going to be each score minus the mean. So it's going to be 89 minus the mean. So it's 89 minus, and then the second recall equals, and I get 12.08 something. Three. And I want to square that. So I can push the x squared button, and it equals, and it's Let's try that again. 89 minus second recall equals, and then push the x squared equals, and that's 146 point something. Oh, 0.06944. Okay, and then the last one, 82 minus second recall equals 5.08 in repeating threes. And then square that, and it equals 25 point something. Okay, and if I total these columns, the middle column should be 0, but because we used rounded numbers, it's a little bit off. We get negative 0.000000004. It's a little bit off because of the rounding. If we had used exact numbers, it should be equal to 0, and you can use that as a check. So it looks like it's right. It's close to 0, and we can account for the difference by rounding errors. And the third column total is really the one that we are going to use, and that's 3,746 point something, and that's what we'll use to compute the variance. So the variance, if we plug it into this formula now, the numerator is just the sum of that last column. It's 3746.916666 divided by, there's 12 scores, 12 minus 1 is 11, so divide that by 11. And that should give us the variance. So 3746.916666 divided by 11, and I get about 340. And I'm going to store that in memory. Do equals 628 78 79. Okay, so that's the variance, and there's some important theorems related to the variance. The standard deviation, we'll get into that a little bit later in the course. The standard deviation is the square root of the variance, and that's also, there's some important theorems related to the standard deviation. So if we take the square root of our previous answer, I stored that in memory. So if we do second square root, second recall equals, I get 18 point something. And I'll store that in memory too. And these were exam scores. They didn't really have a unit of measure, but the standard deviation takes the same unit of measure as the original data. So if the original data was in inches, the standard deviation will be in inches. If the original data was in ounces, the standard deviation will be in ounces, and so forth. Okay, so one of the theorems, related to the standard deviation, we'll get into other theorems later, is that for any data set, at least 75% of the data is within 2 standard deviations of the mean. So for these exam scores, at least 75% of scores should be between 77 minus 2 standard deviations. So 77 minus 18 is 41, and 77 plus 2 standard deviations. 77 plus 18 is 113. So at least 75% of the scores should be between 41 and 113. And in fact, 11 of the 12 scores, or 92%, were between 41 and 113. The only one that was not between those two numbers was the 28. So for this reason, scores that are more than 2 standard deviations above the mean are considered to be significantly different, and the score of 28 is significantly different than the other scores. Okay, so another measure of spread is the coefficient of variation. The coefficient of variation is not used so much, but sometimes it's helpful to compare the standard deviation to the mean, because if you have exams, if you have exam scores of let's say on a scale that are scaled from 1 to 100, a standard deviation of let's say a standard deviation of 5 is maybe moderately spread out, I guess, if the standard deviation is 5. But if you have quiz scores between, let's say, on a scale of 1 to 10 or 0 to 10, then a standard deviation of 5 compared to that scaling is going to be a lot bigger, even though it's the same. 5 is the same for both data sets. So we want to the coefficient of variation gives us a way of scaling the standard deviation to the data set. What we do is it's the standard deviation divided by the mean and then multiplied by 100. So in this case, it's standard deviation is 18 point something, 456, 13144, and divide by the mean, which is 76.91, 91, 666, 667, and then multiply by 100 to make it into a percent. So this comes out to be about 24% according to this. Let's say divide by 76 point. Yeah, about 24%. Okay, there's a in mathematical statistics, if you ever take mathematical statistics, there's a lot of proofs of theorems. We're not going to do a lot with proofs. We'll do a little bit with proofs here. And here's a proof that the sum of the deviation from the mean is equal to 0 for any data set. And that, if you go back to our chart, remember we said that the sum of the middle column should be 0. That you can use that as a check. And here's the proof. Again, with proof, we want to start with the left side, manipulate it to get the right side. So start with the left side. Summation I equal 1 to n, xi minus x bar. By definition of sigma, it's the first score minus the mean, plus the second score minus the mean, plus etc. plus the last score minus the mean. And then we can group the exam scores and the means together separately. So we put the exam score with exam score, mean with mean. That's because the order doesn't matter for addition. This is commutative associative properties of addition. And we have a subtraction here, which is not exactly commutative, but we can treat it like an addition. So subtracting x bar is the same as adding a negative x bar. So if we think of this as an addition, we can change the order as long as we take the minus sign with us. And then repeated addition or repeated subtraction can be represented by multiplication. So if you subtract x bar n times, well, that's the same as subtracting n times x bar. And then this part here, we can go back to sigma notation. x1 plus x2 plus etc. plus xn can be written as the summation I equal 1 to n of xi. So we have that minus nx bar. Use the definition of the mean. That's the summation of xi all over n. The n's will cancel. The n's will cancel. And you just have a sum minus itself. A number minus itself is 0. And that concludes the proof, and that concludes this presentation.